Assalamu alaikum. Hi everyone. In this video, I would like to share how to write a Matlab code to compute the average value, the RMS value, and the power using trapezoidal rule and the Simpsons rule. So there are two major reasons why we need numerical integration. The first reason is the function is known but complicated such that it is difficult to integrate. And the second reason is the function is in the form of tabulated data or tabulated function. That is, the values of the function are known, but the function itself, meaning that the equation, is unknown. So for illustration, I bring in this example that is regarding the half-wave rectifier with RL load. So we are going to compute the average value and the RMS value for the load current, as well as the power absorbed by the resistor, which is the load. So first we assume that the function for the current is known like this, and we will utilize it for the numerical integral. And after that we will see what if the function is unknown, but instead we only have a set of data that describes the currents. Okay, now let's turn our attention on the Matlab script on your right hand side. So here I already created a file with this particular name, and I already list all the values for the constants, you know, the peak voltage for the source, and then resistance, inductance, the angle, sorry, this is the angular frequency, and then theta, the expression for theta that can be found here, and also tau here, and the impedance Z, and also beta. So beta here is actually the extinction angle that need to be solved before computing the average value and the RMS value. So you can refer to my video on how to solve beta using bisection and Newton-Raphson that can be found in my channel. Alright, so here I'm using the function handle to describe the current. So F here represents the current I, and X is in fact equals to omega t. That becomes the angle that is measured in radian. So to compute the average value, the RMS value, and the power, we use this formula, which consists of integral terms, in which this integral will be computed numerically. So notice that this circuit is in DCM, discontinuous currents mode, such that this function is only valid over the interval 0 to beta, not for the whole 0 to 2 pi. The limit of integral must be modified from 0 to beta only. Okay, and these are the formula according to the trapezoidal rule. So if you refer to my previous video, some of these terms, you know, before the braces can be cancelled out, but since the limit of integral is not the same with the interval of a period, so we have to preserve this term. Okay, let's continue with the code. So first we have to specify how many number of subintervals that we want to use. So let's say n, small n equals to 50. So small n is represent the number of subintervals, and then we have the big N that represent the number of data points. So the big N always more one, you know, as compared to the number of subintervals. And then we have to specify the limit of the integral. So let's name the lower limit as x low equals to 0, and then the upper limit x up equals to beta. And also we have to define the width of the subinterval or sometimes we call it as the step size, h equals to the upper limit of the integral minus the lower limit of the integral divided by small n. And then we can generate the data for the angle x equals to, from the lower limit with step size h up to the upper limit of the integral. Okay, so if we run this code up to this line, and let's open the command window first and check our workspace, we can find x appear here, in which the size of x is 51, because the size of x must equals to the big N. Okay, let's continue. So we always like to visualize our data. So by using the for loop, I equals to 1 until big N, and then we can write, let's use y. So y here is actually the currents, because I is already used for the index. I is normally used as the discrete time variable, so do not mix up between this I and the currents in the slide. So now we use I to represent the current, so yi equals to the function of x. And then to visualize the data, we can use the fprintf command, and then normally we like to see a few columns, I, and then followed by xi and yi. So we have 3 columns, in each row. So let's put this 2-digit for I, and then let's say 10-digit with 4 decimal places for x, and as well as for y, and put some enter here. And then if we run this, but don't forget the n, if we run up to this point, so we have like a table consists of 3 columns. The first column for I, and then x, which is the angle omega t, and also the currents. So maybe it's better to have some header here, so copy this, paste it up here, so change to string, and put some to indicate the string. So we rerun this, and then we get the table with header. Alright, so so we continue with the formula according to the trapezoidal rule. So now the real challenge is how to produce the summation of the array. But remember that yi, meaning that the value of the current on the lower limit and the value of the current in the upper limit is not included in the summation. So we can use this technique. So first we introduce one variable, let's say some y, for example, equals to 0, and then we can use for loop again for I until, from 2, remember it begins at 2 up to the small n. So we write, maybe I can put some spaces down here, sum y equals to sum y plus yi, and then we end it with n, and we can get the average value for the currents equals to, so we follow this formula, 1 over 2 pi times h over 2 times y1 plus 2 times sum y plus y big N. Okay, let's check the command window and let's see what do we have so far. So this is the average currents according to the trapezoidal rule, and then we can continue with the finding the RMS value. So basically the idea is just the same, but now we need to generate the expression summation to find the summation of the y squared, again from I2 until small n. So we can modify this. First, let's name this as, put some, wording to indicate this is y squared, and then each element of y must have power 2, and now we have the RMS. So this should be y squared, and then don't forget the square here and also here, as well as the square root. Alright, so let me double check everything. So now we open our command window and let's execute these lines, and then we get the RMS equals to 0.4736. Okay, and finally the power absorbed by the resistor is simply equals to the RMS current. Sorry, this is I squared times the resistor. So highlight, right click, select evaluate selection. Okay, now I'm going to show how to make use of the Simpsons rule to compute these quantities, average value, RMS value, and the power. So actually, when you have the code for the trapezoidal rule, it is not too difficult to modify it to become the computation according to the Simpsons rule. So before that, let me name this to the trapezoid trapezoidal here, and put this one here, and also this one. And then we open this slide first to check the formulation for the Simpsons rule, and then I can copy the whole thing and paste it down here. Now I'm going to modify this code to realize the formulation according to the Simpsons rule. If you notice, the major difference between these two methods is, in the Simpsons rule, the summation is separated into two parts, namely the sum of y with even index and the sum for y with odd index. And again, the boundary values, y1 and y big N, are excluded from the sum. So for Simpsons rule, to compute the sum of yi from I2 and then 2, 4, 6 up to small n, we have to modify this a little bit. Let's say we put some notation here. Sum y even equals to sum y even, and we need to modify the specification for I, because now I is from 2 up to small n, but with every 2 steps. So we have to specify the distance between the index, so meaning that by writing in this manner, we generate I for 2 and then 4, 6, and so on until small n. So similarly for the summation of the odd index, so we modify this, and then here also this one, and don't forget to specify I from 3 and then 5, 7 and so on until small n minus 1. Okay, so we remove this line, and we can get the average current according to the Simpsons rule, and then we follow this formula, 1 over 2 pi times h over 3, and then y1 plus 4 times the sum of y for even index plus 2 times sum y with odd index plus y big N. And I think we can delete this line and then copy this. Okay, for the computing the RMS value, we put maybe y square, or maybe here square SQ here, and then put power 2 here, and for this one we modify the notation and put power 2. Now the RMS value according to the Simpsons rule is the square root 1 over 2 pi times h over 3, and then y1 squared plus again this, replace this, y squared and then square. Okay, and finally the power that is computed according to the Simpsons rule is I RMS squared times R. So let's check the command window and rerun everything again, and then we get the results. So the average current according to the trapezoidal rule has slight difference with the average current according to the Simpsons rule, and then the RMS apparently are equals, and even for the power. Okay, by the way, in general the Simpsons rule may provide more accurate results as compared to the trapezoidal rule. So we can demonstrate this by reducing the number of the subinterval. Maybe if we use 20 subintervals, and then now you can see that there are major difference between the results obtained according to the trapezoidal rule and the Simpsons rule for the average current. And in here, this result is more accurate. So you can refer to the analytic integral to check which results has closer to the results provided by the analytic integrals. Okay. Alright, now I want to demonstrate to you what if the function is unknown, but instead we only have a set of data that describes the current. For that purpose, let's select all and create a new script and paste down here. And imagine that this time we don't have all these informations, but instead we have a set of data that I already included in this folder. So I click open outside Matlab to check the data. Suppose that this data is acquired from an experiment, using some data acquisition devices, for example, with a specific sampling time or the sampling value of the angle. And then we have around, I think, 51 data points, and then how to process this data, and then to obtain the average value, the RMS value, and the power. So I close this first, but first you have to ensure that the file, the Excel file, is included in your working folder. And then the first step is we need to import the data from the Excel to the Matlab. So that can be done by writing something like data equals to XLS read, meaning that we want to read the Excel file, and then inside this bracket, so make sure you write the Excel file name, the exact name, including the spacing, and also the format of the file, XLS or XLSX. So you have to check what is the format. Okay, then if I run these two lines, okay, we have to wait a little bit, and then I have a data, you know, that is imported, that was imported from the Excel file. So the first column is in fact the angle, the second column is the current. So to obtain the angle, I can write x equals to data, and then I want to take all the rows and only the first column, and then y is data, the second column of the data. Okay, even this one we can remove. Maybe all of them first, just remove them. Okay, now we want to know how big the data. So we can write big N equals to the length of X. So if we run up to these lines only, so now I have N equals to 51, you know, based on my workspace. So I can know that I can use the number of subintervals equals to big N minus 1. And the step size is the final value of the angle minus the first value or the initial value divided by the number of subintervals. Actually, I can also get h equals to x2 minus x1, but I think this is more general. And what else? And I think we can use the same code, you know, as follows. But since the power required information of resistance, so we need to have that information. So the resistance equals to 100, you know, because we need to know the power. So if we run this and I name the file as with data, for example, yeah, so this is not required because y was you know, imported from the Excel file. I rerun again. So now I have this tabulated data to visualize them, and then the results for the average current according to the trapezoidal rule, RMS, and the power, as well as the result of the average, RMS, and the power according to the Simpsons rule. So again, to summarize this video lesson, there are two major reasons why we do the numerical integrals. The first reason is the function is known but complicated such that it is difficult to integrate, and the second reason is what we have done just now, the function is in the form of tabulated data. So the function is unknown. We assume that it is unknown, but instead we only have a set of data that describes the functions. So that's all for now. Thanks for watching.